Okay, so let's get started. So people on Zoom, can you give me a signal? Can you hear me? Okay, perfect. Yeah, so let's continue to talk about database systems and how to use a database, and also how to use a database to actually model your application, right? So what do we know so far in this course, right? We spent the first couple of weeks essentially talk about how to use a database system as a user, right? What is the interaction model between user and the database system? And we try to provide the user a really high-level declarative interface such that they can actually manage their data without really thinking about how data is being stored physically, right? So essentially, you have your user on the right-hand side, you have your database system in the middle, right? So under the cover, you have your memory system, and you have your hard drive. And we talk about different ways the user can actually interact with the database system by using different subfamily of SQL queries. You can create a table, right? Once you have that, the database system is going to say, okay, now the user wants to create a table with this schema. And then once you issue a query, right? We talked about that a couple weeks ago and how to write those. And we have 2 hands-on lectures about how to do that. Once you have a SQL query, what's going to happen under the cover is the database is going to bring the piece of data that you want in your query all the way from the hard drive to the memory system and back to you as a user. The goal of building a database system, which we are going to see after Easter actually, is actually how can we make sure as a user on the right-hand side, you never need to think about the thing happen on the left-hand side. The goal is really try to do that automatically as a system. But of course, there are a lot of research goes into that. We are going to talk about how we open up this database black box after Easter. But for now, let's assume there's a magic box, right, going to answer whatever SQL query that you issue to the system. And starting the last lecture, we start to switch gears, assuming you already know about this, and try to think about once you have this amazing capacity of managing your data, what is the right way to think about the process of building a real-world application? Now you have some application you want to build. You want to build the next generation Facebook. You want to build the next generation of the banking system, for example. Whatever application you want to build. How can we think about it? And how can we derive the set of principles that we need to be careful about in how to use the database system to build any real-world application? And that is going to be the focus of what we are going to talk about in the next couple weeks. And in the last lecture, we start the very first step in this 3-phase process of thinking about how to build applications. So let's just try to refresh our memory. So on the left-hand side, you have the real-world application you want to build. The very first phase of building that application is really try to describe precisely what do you mean by building that application, right? What are all the data that I need to model, and what are all the data I need to put into this application? And you want to describe that not in English, but also in something that either machine can understand, and also you can precisely communicate to other people. And this step is called conceptual modeling. And last Friday, we talked about a very specific way for you to do that, which is by drawing an entity relationship diagram. So once you have that, you have a conceptual model of the data that you have. The second step, called logical modeling, that we are going to talk about today, is the process that takes as input this conceptual model, your entity relationship diagram, and map that to your relational schema inside your database. And as we are going to see, given the same conceptual model, there could be so many different ways you can design your logical schema. And as a user, you need to think about what is the right way to do that, and there's a whole bunch of principles goes into that. So once you have your logical design, which is your database schema, the third phase is called physical modeling, and that is actually try to implement your logical schema on a real system. Hopefully, that step is going to be done automatically by the database system. Now let's look at one concrete example, right? So we looked at that before. Let's try to refresh our memory. So assume you want to build this application, right? So concretely speaking, right? So I can write down an English description about what we mean by all the data we put into the application. There's a product, right? So that's part. Each part has a whole bunch of kind of properties. So very first step is to take this kind of vague and imprecise description in human language and write that down precisely as a conceptual model. Once you have this, the machine can understand what you want to build, and other human can understand what you want to build. There are so many ways of doing this. One Swiss way is by drawing an entity relationship diagram that looks like this. And the second step, the logical modeling precisely, is to take this diagram that contains a conceptual model of your data and try to map them into relational schema, into whatever data model that you want to map to. But in this course, we talk about relational model. And then the third step, the physical modeling part, is to take as input this logical model and map them into, for example, a sequence of 0 and 1s on your hard drive, right? So that's when you physically actually implement this data model. So hopefully this step will be done automatically by the database for you as a user. So in this lecture today, we are going to first finish up something that we left out about conceptual modeling, right? And then once we finish that, we are going to talk about how to map that entity relationship diagram to a concrete logical data model. And also, what are the trade-offs? What are the things you need to consider carefully when you are do such mapping? How to reason about what is a good mapping, and how to reason about what is a bad mapping, and and how can we make a decision by picking the right point in the trade-off space. So now let's continue to talk about conceptual modeling and continue to talk about entity relationship diagram. So we talk about multiple concepts here, right? We know what is entity site, right? We know what is attribute. We know how to draw relationships, right, between those entity sites. We talk about the notion of key. We talk about role. We talk about cardinality, right? So just try to refresh our memory, right? So once you know this concept, right, you should be able to read this entity relationship diagram pretty easily, right? So what do we know in this application? Yeah, we know in this application that we want to build, there's a whole bunch of entities or objects that I want to manage. There's a whole bunch of students, a whole bunch of lecturers, assistant, and professor, right? Each one of them corresponding to one entity site in this diagram, which is all those rectangles that we have. And for each of those entity sites, I also know they have attributes associated with them. A student has a name. A professor has a personnel number, for example. You can draw them, right, for each of those attributes into those small circles, give a name, and link that to the corresponding entity site. And we also know in these applications, we need to encode relationships between different entity sites. For example, there's one relationship called attends, connecting students and lecture, right? Students attends lecture. So once you know those concepts, it's very easy to see precisely what we want to build inside this application. Another concept that we talk about is cardinality, right? Which is essentially how many times an entity can participate in a given relationship. For example, you have a relationship connecting professor and lecturer, and you say, in this application, I know, for example, one lecture can only be taught by a single professor, right? Which means that a unique lecturer can only participate once in this relationship. You cannot have a valid database instance that the same lecture corresponding to two different professors. So how to encode that information? And we talk about one notation to express that is by having those labels of 1 and n, right, whenever you have a relationship connecting to an entity site. And we also talk about the formal semantics of this, right? By having this notation, what do we mean by this? the way to think about it is to go back to the formal definition of what we mean. Essentially, for every single edge with a label 1, it means that if I know the rise of the entity set, I can uniquely define or corresponding to a single value of that entity set. For example, here, if I look at entity set A, right? So the connection between A and R, there's a label 1 there, right? It means that for every single unique combination of B, C, and D, they can only appear once in this relationship. I cannot have two combinations of the, I cannot have the same configuration of B, C, and D participated twice, but linked to different value of A. Okay, so that is what we mean by this. And similarly, for the edge between R and C, right, you see there's a label 1 there. It means that if I take a configuration for the combination of A, B, and D, you take the other entity set. If I know the value of A, B, and D, I know precisely a unique C entity that participate in this relationship. Okay? So this is what we mean by this notation. Essentially, it's trying to define, the cardinality try to define a whole bunch of conditions that a valid database instance need to satisfy. Okay? So cardinality are somehow a little bit tricky. If you think about an entity relationship model, that's probably the most tricky thing. And when we talk about the logical modeling, that's also have a very big difference in different logical design, right? Because that's going to introduce redundancy. And that's kind of the core that we are going to talk about today and on Friday about how to do this logical mapping. So it's very important for us to understand this precisely. So once you have cardinality, right? So underneath the cover, what we are saying is, now I give the condition of what is possible in this application. So now let's take this concrete example and try to think about whether the following database instances are possible. So we went through this exercise last week. I really want to make sure we are on the same page about what we mean by cardinality, okay? So let's do it again. Now we have these 3 different entity sets. We have students, we have professor, we have topic, okay? And there's one relationship R connecting these 3 different entity sets. My cardinality is, for students, I have label N, and for professor, I have 1, for topic, I have 1, okay? So what do we mean by this? If you take the 1 label connecting R and the professor, it means that a combination of student and topic can only participate once in this relationship. If I know the value of student and topic, I know which professor is associated with that pair, okay? Similarly, if you look at the label between R and topic, it tells you, yeah, a combination of student and professor can only participate once in this relationship. If I know those values, I know the value of topic. So now let's look at whether this database instance is valid under this conceptual model. Right? So in this case, what do? You check. You check whether student and topic pair participate at most once, right? So in this case, student 1, topic 1, student 1, topic 2, they are different, so it's fun, right? And you look at the other way around, you look at student and professor, right? In this case, you have student 1, professor 1 appear twice in this instance, right? So that's violate our cardinality constraint, because even I know the value of student and professor, I know the student 1, professor 1, I don't know which topic is associated with that, right? I have topic 1, topic 2, right? I don't know. So that's violate this cardinality constraint. So similarly, look at this example, right? Student 1, professor 1, topic 1, student 1, professor 2, topic 1, right? So again, go back to the definition, look at every single edge in your ER diagram with label 1, okay? Look at the professor, that's label 1 there. Look at student topic. In this case, I have student 1, topic 1 appear twice. That violate the kinetic constraint. Similarly, we have this another database instance You have student 1, professor 1, topic 1, student 1, professor 2, topic 2, right? So is this valid? Yeah, again, go back to definition. Look at all the student topic pair. In this case, student 1, topic 1, student 1, topic 2 is okay. Look at all the student professor pair, right? Student 1, professor 1, student 1, professor 2 is okay. Okay, so this one's valid. So, and again, you can go through the same exercise, and this one is also valid. So it's very important to get on the same page about what do we mean by cardinality. So any questions so far before we talk about anything new today? This is something we have talked about last week. I really want to talk about it again to make sure we are on the same page. Any questions? Any questions? So there's one question on Zoom saying that relationships are always symmetric relations, right? I'm not sure what you mean by symmetric. Yeah, so like you can unmute yourself and speak up, and we should be able to hear you. Yeah, what do you mean by symmetric? Okay, interesting. So essentially, the question is, if I have a relationship R, and I know entity A and B participate in this relationship, whether I know the other way, like B and A also participate. Not always, right? So think about the relation R as, for example, parent of, right? So clearly, A and B participate doesn't imply B and A participate, right? So it doesn't need to be symmetric, yeah, in that way, okay? Yeah, so they could be integrated in the diagram, so you can have different roles, right? So that's why we have the notion of role, right? You can have, say, yeah, there's two entities participate in the same relationship. One is parent, another is child, right? You can actually have a label on the edge if you want to encode that, right? Make sense? Okay, so any other questions? No? Okay. Now we know about cardinality. When you go back home, try to read this by yourself. Okay, there are a lot of things here, but it should be relatively easy for you to understand this part. Okay. So now we introduce a specific way to specify cardinality, and there could be other ways for us to specify cardinality, and sometimes they are actually more expressive. So instead of labeling the edge with 1 and n, right, 1 and many, right, you can actually be more precise about what you mean by many, right? How many times, right? So there's actually a specific like notation for you to do that, and it is a min-max notation. So essentially what you are going to do is you can actually have the min and the max value labeled along like each of the participation of each entity set in each relationship. For each edge, you can say, this is the minimal number of times that an entity can participate in this relationship, and this is the maximum amount of time that the same entity can participate in this relationship. Okay? So if you think about what is the formal semantic of this, what are the database instances that are valid under this notation, essentially for every single cardinality kind of min and max value, you are essentially specify a very precise logical constraint. That is, for every single relation, right? So you can find uniquely, okay? So there are going to be exist kind of at least minimum amount of time, and at most the maximum amount of time. You can find that like that many participation of the same entity in this relationship. Okay? So it's very precise about what we mean by this. So one thing that's easy to see is the min-max notation is more expressive than the one-to-many notation that we saw, because you can express any of the one-to-many constraint with the min-max notation, right? So assuming we have this constraint, we have professor and the course, right? So we have the 1 connecting course and teachers, and we have n connecting professor and teachers. So to express this in this alternative notation, you can have 0, 1 connecting professor and teach. Means that for every single professor, it can appear either 0 times, or can appear can participate once in this relationship. Okay, you cannot have a case that the same professor participate twice in this relationship, which is essentially what the diagram on the left-hand side was talking about. Make sense? Is the equivalency between these two clear? Any questions? Okay. So now let's look at one concrete example. So assuming we want to model these objects, okay? We want to model all the polyhedron in the three-dimensional space, okay? So we have an entity, for example, a polyhedron, a whole bunch of those. And each of the polyhedron, we have a surface, whole bunch of surface, and they together form a polyhedron. And then we have each surface is defined by a collection of edges, and each edge is associated, is defined by 2 nodes in the three-dimensional space, right? And for each node, I have the x, y, z kind of coordinate associated with that. So let's look at this and try to think about what cardinality constraint that we should put here. So here I already show you, right? So the one-to-many thing. So what do we mean by this? So we look at the connection, the relationship between surface and the polyhedron, right? So if you do the one-to-many notation, I think something that's reasonable here in three-dimensional space, right? It's actually you have the 1 there. So there's a many-to-one relationship from surface to polyhedron, right? Which means that if I know a surface, right, so I can uniquely identify a polyhedron, okay? So, and then if you think about what are the relationship between surface and the edge, right? So, I mean, it's kind of like many-to-many, right? So in a polyhedron, if I know an edge, I cannot uniquely identify a surface because there could be 2 surfaces sharing the same edge, right? And the other way around. So the only thing I'm able to say between surface and edge is there is a many-to-many relationship between these two, okay? And if you think about the edge and the node, right? So that's the same thing, right? So I look at the node on the corner, right? So that's kind of intersection between 3 different edges. Given the node, right? So I cannot identify a unique edge. And given an edge, of course, I cannot identify unique node because I have 2 of those, right? So there's a many-to-many relationship between edge and node. So this is one specification of cardinality that actually makes sense in our three-dimensional space. An alternative way of modeling this using different notation is by doing this min-max notation, okay? And this is where you are able to encode more information, and we are able to see it now. So let's look at the polyhedron and the surface, right, relationship. How many times can a single polyhedron object appears in this relationship or participate in this relationship? Well, in three-dimensional space, right, a single polyhedron have at least 4 surfaces, right? So it can have more, but it cannot have 3 because then it's not closed, right? So in this case, a valid database instance should have a single polyhedron appear at least 4 times in our three-dimensional geometric space. And then you can have the min-max notation here. You can have the 4 there, saying that the minimal 4 times, okay? You can participate more, but at least any valid database instance, I should see the same polyhedron appear there at least 4 times, okay? So as you can see, you start to include more information than the one-to-many notation, right? And then let's think about surface, connecting polyhedrons and surface. Yeah, so let's look at that relationship. For every single surface, right, so it can participate once, right, because it can only be like there for like a one polyhedron, right? So there's no like intersection there, right? So you have this surface. If you think about surface and polyhedron, right? So there's it appears once, right, and only once, right? So and if you look at between surface and edge, so what do you have? For every single surface, how many times does it need to participate in the boundary relationship, right? So in this case, you'll say, yeah, this surface have this boundary as an edge. So in this case, right, for every single surface in our three-dimensional space, it need to have at least 3 different edges, otherwise it won't become a surface, right? So for any valid database instance, you need to have the surface appear at least 3 times. It can have more, right? You have like rectangle as a surface, yeah, fun, but you have 4 different edges there. It need to appear at least 3 times, and we don't know the maximum. It can participate however many times it wants, right? So, and then if you look at the thing connecting edge and the boundary, right? So that's actually 2 and 2, right? So for a single polyhedron, for every single edge, it need to be on the boundary connecting 2 surfaces and only 2 surfaces, right? So a single edge participate twice and only twice, okay? And then if you look at the connection between edge and the start and end with a node, right? So that specifies you have an edge, this is the starting node, this is end node, right? In this case, how many times can a single edge participate in this relationship, right? It's 2, right? So a single edge have 2 nodes. I mean, I cannot have a single edge corresponding with 3 nodes because I don't know what that means, right? So in this 3-dimensional space, so it can participate twice and only twice. And if you think about a node, right? So in a polyhedron, right? So it participates at least 3 times because that is actually the corner node, right? So it connects 3 different surfaces. You cannot have a polyhedron where a node connecting only 3 only 2 edges, right? So you won't able to close it in our space, right? So and then it can participate as many times as possible, right? So as you can see, these are the 2 different ways of specifying cardinality. On the left-hand side, you are specifying this as many to one or many to or one to many, those type of things, right? So on the other hand, you are specifying precisely how many times a single entity can participate in which of this relationship. And it's also very easy to see that the min-max notation is more expressive than the one-to-many notation. For any one-to-many notation, you are able to express it using the min-max notation. But on the other hand, if you do the min-max notation, you are able to encode information that you cannot encode in the one-to-many notation. So far, so good, right? Any questions about these 2 different ways of expressing cardinality? Any questions? Do you have questions? Sorry? Okay, yeah. Okay, great. If you have any questions, right, so just let me know. Okay, that's about cardinality. In your entity relationship diagram, you can actually do more, okay? So another thing that's very important in real-world applications, when you try to model it, is called a weak entity, okay? So what do we mean by this? So far, when we talk about entities, we always think about those entities as things that can exist on their own. We talk about professors, we talk about students, right? So they are the objects that exist. So there could be entity whose existence relies on other entities. For example, you could have one entity which is a building, like this building, contains a whole bunch of classrooms, right? So there you have 2 entities. You have the building entity, you have the classroom entity. If you think about these 2 different entities, their relationship is a little bit stronger than the relationship between professor and students. Professor and student can exist on their own. They can participate in different relationships, right? But they exist on their own, right? But if you look at building and room, a room cannot really exist if it's not in a building. So there's a strong relationship between whether one can exist. So the existence of some entity might rely on other entities, right? So room relies on building. And how can we really encode that? So in this case, we can introduce the notion called weak entity, right? And you can say, okay, I have an entity called room, and I have an entity called building. Room is a weak entity, relies on building. So the way to encode that is by having this kind of double rectangle thing and double diamond, right? And to specify, okay, room is a weak entity, and it relies on a building via the located relationship. Okay? So the consequence of this is that whenever you are talking about the key of a room, it's going to have the weak key, which is the room number, and also the combination of that with the key of the building. Whenever I talk about room, I need to talk about which building it is and also which number it is. Okay? So, and that's the implication of doing something like that. Whenever I have a weak entity, the key of the weak entity is going to be the direct key associated with the weak entity, which is the room number here, and also together with the key of the strong entity. Okay? So in this case, the key of the room is going to be the building number and the room number, this combination. So another thing is, what is the cardinality of this located relationship, right? So it's going to be many to one from room to building, because if you talk about single room, right, that can only belongs to a unique building, right? So that is actually what you are going to have when we talk about weak entity. So this also implies, right, so there's cannot be a room without a building. Whenever you are drawing this, you are telling the other people, I cannot have a room without a building. So that is what implied by having room as a weak entity relies on the strong entity building. Okay, make sense? Is this clear? Any questions? Okay. Now we have more in entity relationship diagram. So there's another thing that you can draw in your conceptual model to specify other type of relationship between entity sites. And one is about generalization. Okay? So here, in our university schema, right, we talk about there are students, right, there are professors, there are assistants, right? But to some extent, they are all person, right? So there's a different level of entities in the real world application. And how can we encode that? The way that you could encode it inside your conceptual model is by introducing this type of hierarchy with a special type of relationship. People give that different name, but here you can say here's is-a, right? So that's relationship with that very beautiful hexagon there, right? So to really specify this spatial relationship between those entity sites. So essentially here you have this person entity site, right? And then you have professor and students. They are being connected by this is-a relationship, which means that professor is a person, student is a person. Okay? And then you have the direction of the edge, right? From professor to person, from student to person, right? So corresponding to the direction of the hierarchy, right? Professor is a person, student is a person, okay? And then what this implies is that both professor and students, they will inherit, so they are going to have the same key and same attribute as person. Whatever attributes you have for a person, it's also going to apply to professor, also apply to students. You could have spatial attributes corresponding to professor, special attribute corresponds to students, but they are going to take all of the other attributes and also the key from the person side. Make sense? This makes sense, right? Any questions about this? No? Okay, great. So this is actually all the concepts that we are going to talk about for conceptual modeling. I mean, in practice, there are actually way more than this, okay? Whenever you are building a real application in real world, when you have things that you want to model, but you don't know how to map to any of the concepts we talked about so far, highly likely that thing exist like in the standard. Okay, so just I hate to say it, but just try to Google it. Right? How to model this in entity relationship diagram? Highly likely you are able to find it. Okay, so entity relationship diagram is a language with a very rich semantic, and we only talk about those kind of like very small part of it. Okay. Another thing when you really see conceptual models in real world is to keep in mind that there are many different flavors of entity relationship diagram that you are going to see in practice. So just do not be surprised when you see something that looks different. Okay? For example, we talk about this many-to-one relationship, this notation, right? In practice, you are going to see, yeah, maybe this many-to-one is encoded by the direction of the edge. You also see that. And they are talking about the same thing. Okay? You are going to see things like this. Like in some system, you are using this special notation, right, to encode this many-to-one relationship. You are going to see different flavors of entity relationship model in practice. Just do not be surprised. Okay? So in the exam, in this course, right, so we will stick to what you see during the lecture, right? But in practice, do not be surprised when you are seeing something look different than what we talk about in the course. Okay, so no way we can enumerate all of them, but just don't be surprised. And whenever you see something you do not know, just try to Google it, and highly likely the answer is there. Okay. So now we have another 8 minutes, right? So let's try to do a little bit of exercise and try to read an entity relationship diagram together. It's very important that we are on the same page about what conceptual model is, because because otherwise we don't know how to map that to a concrete relational schema. So this is just what I just take from Wiki. Okay, if you go to entity relationship model, you'll see this on Wikipedia. It's actually try to encode, I think, a game. Okay, so there are different characters. So let's try to read this together. Okay, so what do we have here? So we have 7 entity sets, right? Because there are 7 rectangles there, right? So there are entity sets. There's we read it from the left-hand side, right? So there's account. There's a whole bunch of account user can have in this gaming system, right? Each account associated with a whole bunch of character, right? And then there's region, there's item instantiation, right? So a whole bunch of other things, right? So you have those 7 different entity sets, okay? And then if you look at these 7 entity sets, they are also different. There are strong entities and there are weak entities, right? So here you have 4 strong entities, which means that they can actually exist on their own. There's account, there's a region, there's item, there's creep. There's 4 strong entities if you look at this diagram. And then there are 3 different weak entities. For example, there's character, the character you have like in the game, right? Which is a weak entity relies on the account connected by the has relationship. If you look at what this really means, it means that, okay, so I can have a whole bunch of characters, but each character must be associated with an account. I cannot have a character exist without an account. Okay? So that's what it's trying to say by having character as a weak entity. And then there's a whole bunch of relationship connecting them, right? And then for each one of them, there's a cardinality label, right? It should all make sense at this moment, okay? So when we go back home, try to look carefully at this diagram and try to think about what is actually trying to encode, okay? So another thing is, when you are having some application you want to build, when you are doing this conceptual modeling step. So far, if you think about what I've been talking so far, we seem to give you an impression that the conceptual model part is relatively well-defined. Taking the same application, different people might give you the same conceptual model. But in practice, when you talk about real application, it's actually more complex than that. For the same application, there could be so many different ways that you can design it conceptually. Different people can give you different entity relationship diagram for the same application. So that's quite reasonable. So because of that, we need to think about what are the principles? How can we think about a good conceptual model or bad conceptual model? And given one application, how can we systematically apply those principles to get a conceptual model that's good enough? So we can only give you principles because the real world is really complex, but there are some principles. So, and if you look at them, it actually makes sense, right? So a good design should reflect reality, okay? So this is very important. Whatever you are doing, right, need to reflect reality, need to reflect what you are really trying to encode, okay? So, and the second thing is, often we want to avoid redundancy during the conceptual modeling thing. We want to model one piece of data, ideally only once, okay? So for example, given the assistant and professor, like these two pieces of data, right? So if you say, yeah, so how about for each assistant, I also have another attribute called advisor, which is the professor that this assistant works with, right? So in this case, you have this redundant piece of information in this conceptual model, right? So that is something in practice we hope to avoid, especially at the conceptual modeling part. So down the road, when you are really trying to optimize your application, like we are going to see in some cases, you want to introduce some redundancy to make sure your system is fast, okay? But highly likely, you will not do that in the conceptual modeling part. During conceptual modeling, try to avoid redundancy as much as possible, okay? So another thing is keep that simple, right? So if you can model something with a single relationship and that give you all the information you have, that enforce all the cardinality that you want to enforce, go with the simple one, okay? So try to make sure that you do not have multiple of those relationships, but at the end of the day, you are modeling essentially one relationship, okay? So there are several rules of thumbs here, right? So for example, how can we think about attribute and entity, right? Whether I should model something as an attribute, or whether I should model something as an entity and connecting that with another entity with a relationship, right? So it's very hard for you to have kind of a hard rule to say you always do that. It always depends on your application. But there's some quick rule of thumb, right? For example, often like you should model something as an entity, right? If that participate in like more than one relationship, right? So if you have something that only have one-to-one relationship with an entity, yeah, maybe think about whether it makes sense to have that as an attribute instead of as an entity, right? So the whole bunch of those rule of thumbs, right? So, and sometimes in practice, when I'm modeling real applications, your ER diagram could become really, really big, right? We look at those, they all fit on a single piece of paper. But if you think about modeling every single entity, right, in a single university, it's going to be a very big thing, right? So here, try to think about how to partition like your ER models, right? Maybe have something, for example, if you talk about university, maybe have one conceptual model for library, right? Maybe have another conceptual model for research things, for finance, for example, right? So automatically partition it is very hard because the optimal partition relies on your application. But try to think about it when I'm modeling the real thing, okay? So there's a difference between a good conceptual model and a bad conceptual model, right? Try to avoid redundancy, right? Try to decrease the amount of entity you have. Try to decrease the amount of relationships that you have in your conceptual model, if you are able to build the thing that you want. Okay? So there are a lot of those tools to create ER diagrams. So we talked about that last week. You can actually draw a whole bunch of rectangles and circles, and you have ER diagram, right? And then you can actually play with it by yourself, right? So, and what people usually do is they will actually design an ER diagram, and that tool will try to automatically generate a relational model for you. Okay? So that's the first half of the lecture today. So let's take a break for 15 minutes, and then when we get back, we are going to take our simple ER diagram and generate a relational model. Okay? Yeah, so we got a very good question during the break, right? So I was talking about the relationship between the min-max notation and also the one-to-many type of notation, right? I was saying the min-max is more expressive than the one-to-many thing. That's only hold when you only have those binary relationships in your ER diagram. When you have those like multi-way relationship, it's become trickier, right? So then there start to have things that you can express in the one-to-many in the one-to-many notation that you cannot express in the min-max notation. Okay. So, but the statement hold when you only have binary relationships in your ER diagram. Okay. Okay, great. Now we understand how to do conceptual modeling. Right? Given one application, how can we actually model it using an entity relationship diagram? Now let's try to talk about the second step to model your application. And that's a step that we call logical modeling. So in this stage, you already have your entity relationship model, which is this diagram, right? But we want to translate that into a relational model, right? Such that you can actually start to implement that inside your relational database. Essentially, we want to understand the process that take us input this diagram and try to output a relational schema. There are so many different ways you can do it, and we want to understand which is a good way, which is a bad way, and how to think about it. So just to refresh our memory about relational model, right? So we are talking about this is an instance of relational model, right? It's a whole bunch. You can think about that whole bunch of tables with content, right? So whenever I'm saying that we query it, right? So we try just the signature of a query. It takes a simple instance, output a new instance, right? And we talk about different ways you can express your query. You can express that using SQL query. In practice and on the theory side, you can do relational algebra. You can do relational calculus. So now we have an entity relationship model. Now we have a relational model. How can we do the mapping? The principles are kind of easy to state. Whatever entity set you have in your entity relationship model become relations in your relational model. Whatever relationship you have inside your entity relationship model become relations. That's not surprising because all we have in relational model are relations, right? Essentially, pretty much entity set and relationships all become relations. And then whenever you have relations that share the same key, you can merge them. We are going to look at why that happened, but whenever you have something that shares a key, you can actually merge them. There's some special consideration you need to take when you talk about generalization, when you talk about weak entities. But this is the principle. It's very easy as a principle, but let's try to look at different corner cases when you just apply all those principles. So entity set become tables, and attributes of entity set become attributes of that table, okay? So assuming I have this entity relationship diagram, I have employee, okay? And then I have three different attributes. I have one attribute called SSN, which is the key, the primary key. Then I have another attribute name, an attribute of age. So how should we translate this very simple diagram into a relational model? This is a case that applying those principles are actually easy, right? Entity set become a relation. Right? Here we have the employees relation in our relational model, right? So try to encode the employees entity set in the ER diagram. And the attributes of the entity set in my ER diagram become attribute of this relation in my relational model. I have three attributes in my ER diagram. Here I have three different attributes in my relational model, SSN, name, and age. And my primary key is SSN, which is the primary key you have in your ER diagram. So far, so good, right? So this is a very simple example how to do the translation, okay? So, and whenever there is no cardinality constraint in your ER diagram, the whole thing is actually like easier. Okay? So in this case, each of those relationships will become one relation containing the keys of all the participating entity site in the ER diagram. So let's look at one concrete example. Okay? So here I have an ER diagram with 3 different entity sites. Okay? I have employees, I have locations, I have, for example, departments. The 3 different entity sites. And employee has a key, SSN, location has a key, address, department has a key, department ID. And they have their own different attributes. And they have a single relationship connecting all these 3 different entity sites. Works in employees, works in this department, in that location. Okay? And then there's an attribute associated with the works in relationship. How can we do the translation? Well, the translation of each of the entity sites should be clear, right? You should have one employees table contains SSN, name and age. You should have a locations table contains the address. You should have a department table contains department ID, budget, and department name. So let's focus on the thing in the middle, the works in relationship. So when there's no cardinality constraint, that step is simple. Okay? So you create a relation here called works in, corresponding to the works in relationship in the ER diagram. And what are the attributes of this works in relation? It should have the keys of all the entity sites that this relationship is connecting in the diagram, which makes sense, right? So this relation is used to store information about how employees and location and departments connect to each other, right? In the logical model, in the relational model, it should contain the key of the employee, the key of the location, and the key of the department. That's pretty natural, right? And then it also contains whatever attributes you have in the ER diagram associated with that relationship. Here, the working relationship has a since attribute. In the translation, you will also have another column or attribute for this relation called since, right? So far so good. Any question about this? No? Okay. Now let's look at this. What are the, after translation, I think it's very clear what are the set of attributes we should include after the translation, because yeah, it's very natural. But what are the primary key of this works in relation? And that becomes a little bit tricky. What are the primary key for this one? If you do not have a cardinality constraint in your ER diagram, the primary key of this works in relationship is going to contain 3 different attributes. It's going to contain SSN for the employee, address for the location, department ID for the department. It's going to be the combination of these 3. That's going to be the primary key that you have for the works in relation in your relational model. That makes sense? Why? Because in this ER diagram, I do not have cardinality constraint. Every single employee, every single department location can participate 0 to however many times they want to participate, right? So essentially, the instance I'm defining by this ER diagram can have essentially all the possible triples among these 3 different entity sites, right? And that's translated into this primary key in the works in relation. Okay? The only thing that is unique in this relation that I'm sure about is a combination of these 3 different values. Okay? So that is why after translation, if you do not have any cardinality constraint in your ER diagram, if all the relations are many to many, after translation, the primary key is going to be a combination of all the keys that you have, like all the keys of all the entity sets that participate in this relationship. Make sense? So far, so good? Okay. It's going to get a little bit trickier once you have cardinality, okay? So it's very important to get this right. We agree, right? Who thinks this makes sense? Who thinks this doesn't make any sense? Okay, perfect. Yeah, so why is the key? It's very important, okay? Once you have roles inside your entity relationship diagram, right? So the translation also pretty natural. So assuming you have employees, this entity side, and you have another relationship called reports to. Some employee reports to another employee, for example, right? And of course, right, so you have one relationship connecting two entity sides, you need to give the role of their participation, right? Some of them are supervisor, right? Some of them are not, right? You put those labels there. When you do the translation, those roles become the name of the attributes, okay? So here, once you do the translation, the reports to relationship in your ER diagram going to become another relation. Sorry, not another. Like going to become one relation in your relational model. Reports to. There's going to be two different attributes there. One corresponding to the supervisor's SSN, right? So that is the key of the employee. The first one, you just label the attribute name with the role that this attribute that's inside have in the relationship, right? You have another which is subordinate SSN, right? So then you can distinguish these two participations. So far so good, right? Okay. What are the primary key of the reports to relation in this case? I already labeled it, right? So we kind of know the answer. But let's try to think about why. So in this case, I have no cardinality constraints for the reports to relationship, which means that if you think about what are we allowing as a valid database instance, I can have all the possible pairs there, and I put them in as a valid database instance. So which means that the minimal set of attributes that is unique in the reports to relation is actually these two keys combined, right? So I do not have, I mean, the relationship is many to many. After the translation, I need to include all the keys of the participating entity to form the new key of this reports to relation. Okay, make sense? So far so good, right? This is natural. Okay. Cardinality can be tricky, okay? And we are going to have a lot of fun about it. Now let's look at this relation. So it's the same as before. Now we start to introduce cardinality constraint into this. Now I have a simple one, okay? So I have the one-to-many notation. I say there's a one label connecting department and works in. What does this mean? This means that I'm only allowing a subset of database instances in this application. And those I allowed is that a unique value of location employee can only appear once in this relationship. You cannot have the same location employee mapped to two different departments, right? So that's what we mean by this. How can we do the translation? Can we do the translation like this? If you just take the principle and say, yeah, the working become a working relation, if we still have the combination of the keys from all the participating entity sites as a key. If you have the SSN from employee, department ID, address from location, combination as a key, is this still correct? So we write that down, it's not correct, okay? But who agree it's not correct? Who are not sure why it's not correct? Exactly, okay, perfect. So now let's think about what are the implications of the cardinality constraint. From the cardinality constraint, what do I know? I know that in this relation, I will never have the case that I see two tuples with the same location and employee value, but associated with a different department value. It means that if I know SSN of the employee and I know the address, I can uniquely identify a department. Make sense? That means that this subset of attributes containing 3 different attributes for the SSN, department address, they are not the minimum subset of keys that identify a tuple in this relation. Make sense? So these 3 attributes together is not a key because they are not minimal. The reason they are not minimal is because of this cardinality constraint you have in your ER diagram. Make sense? Now, who agree this is not correct? Okay? Who are still not sure this is not correct? This is very important, guys, to make sure we are on the same page because it's getting trickier after this. Okay? Perfect. Now, let's look at another example. Let's look at this one. How can we do the translation? Now we have the employees, we have departments, right? So we have this many-to-one relationship from employee to department. How can we do the translation works in, right? Now let's consider these 2 relations, right? So we first do the translation of employee, right? Now we have this employees relation. The primary key is SSN, right? That's the primary key of the employees, and then we have the attribute name. And when we do the translation works in, I think we all agree it should look like this, right? So the primary key should only be about employee because there's a many-to-one relationship from employee to department. If I know the employee, I know which department that employee works in, right? So after translation, the works in relation is going to have the primary key solely depends on the employee, not the combination. Okay? Now let's look at these 2 relations. They actually share the same primary key, right? So can we merge them? Can we merge these 2 into an even bigger relation? Because they all share the same key, right? They're all about a single employee, right? I could have merged them into a different relation that's bigger, contains SSN, the name, the department ID, and the since attribute of the works in relation. Both make sense, right? But what are the benefit of the disadvantages of merging these 2 things? Yeah, let's try to think about this. This is interesting because now we have 2 different logical designs of the same ER diagram, right? How can we compare them? How can we think about the trade-off? Right? There's no universally good design, universally bad design. It's always about trade-off. Before merging, after merging, what are the benefit? Who want to try? So one benefit of merging them is, I mean, there are multiple of those, but one thing is you start to have, first one, less redundancy, right? So second one is smaller, for sure, because the first one I have to store the SSN twice, right? For the second one, I have a smaller database, and not by too much, but smaller, right? So that's one thing. There's fewer amount of redundancy. What are other benefits potentially we could have? Yeah, exactly. So the second one have better locality, right? So if for every single employee, you need to have their department, when writing a SQL query, for the first design, you need to join them together. If all the query you are ever going to write in this application always contain that join, I mean, the second one will be way faster because you are running one fewer operator in the second design. Right? You start to see the difference of how logical design is going to have impact on your performance, right? So it has better storage efficiency, right? It's more efficient in terms of the storage. It has less redundancy. It has better locality. What could be the disadvantage of merging them, right?
If you have a bunch of employees that aren't assigned to a department yet.
Yeah, exactly. When you have a lot of employees who does not have a department, right? So what can you do in the second case? You are going to have a whole bunch of null values there because I don't know the department, right? So that could cause multiple problems. The first one is probably the less important one is going to be maybe bigger than the first one, right? So because it have all those holes in the table that I need to store. But for the first design, if an employee does not have a department, I do not need to care about it at all. I do not need to store any information there, right? So depending on your application, your assumption on your application, it's not really clear which design gives you a bigger database, right? That's something you need to be really careful about. And second, if you have a relation with a lot of those null value, that can actually make the querying processing step a little bit fuzzier for user. You need to think about, there are a lot of nulls there, right? So that's something to think about. So again, so this is one simple example, right? This is probably the most kind of simplest ER diagram that you can draw. But even this simple one have multiple alternative design on the logical side. And when you build a real application in real world, it's going to be even more complex than this. But again, like think about whether to merge them or not, okay? So it's very hard to reason about what is better design than the other, but sometimes it's easier for you to reason what is definitely a very bad design. So now let's look at another example. Again, I have the same ER diagram with employees and department. So now let's think about these two relations. The first one corresponding to department, right? I need to have this, right? For this department, I have department ID, I have budget. On the other hand, I have this works in relation. Can I merge these two? Can I merge these two into a bigger relation that contains information about employee, also contains the information about department, right? So I try to merge the relation corresponding to department and works in, which is different from the previous slide. In the previous slide, I try to merge works in and employee. So let's look at these two alternative design and reason about which one is better. This is an easier case to compare because the second one is clear is actually not that good, right? In the previous slide, it's very hard to say which one is better because that's different application. This one, second one, pretty much definitely, in many cases, actually definitely going to be worse than the first one. Why? Who agrees the second one is worse? Who agree? Who think the first one is worse? Who don't know? Okay. So in this case, what is the reason that so what could be the potential problem after merging these two things together? So one thing that's important is these two relations do not share the same key, right? So they do not share the same key. One is about employee, another is about department. So essentially, in the works in relation, you could have the same department appears multiple times, right? I mean, one department hopefully have more than one employee. And in the Cardinality constraint, all I'm saying is one employee become to, is part of one department. That's clear. Not the other way around. One department can contain multiple employees. If you look at the works in relation, in most of the applications, I hope is you are going to see the same department ID appear multiple times, okay? And then if you merge these two relations, you are going to store all those information about the same department multiple times too in the merged relation, right? Because for every single department, I need to store its budget. But since I'm merging that with a works in relation, the same department can have multiple rows, and for each of those, I'm saving the same piece of information. Make sense? So what is the problem of that? Exactly. So the least important problem is that relation going to have a lot of redundant information, going to be bigger. But the more important is you start to introduce those potential problems of data integrity, of data consistency. Once you are storing the same piece of information multiple times, you need to make sure whenever someone updates it, it's also going to be reflected in all the appearance that it has in your data. If you are duplicate the budget information multiple times, will increase or decrease the budget of that department, you need to update all the possible tuples there. It's going to be slow, which is actually not that, which is very important. But the more important thing is, it's very easy for a user who do not fully understand your assumption to get something wrong. Maybe they're a user who actually forget about updating all the tuples. Then you have a database that have inconsistent data, and you don't know what is the right budget anymore. So that's actually going to hurt you a lot in many applications. You will suffer in data correctness. It's going to be more expensive to implement the right query. And of course, it could be bigger because you have those redundancies. On Friday, we are going to think about mathematically how should we talk about those redundancies. But this is just to get a feeling that this is a case that you definitely should not merge two relations. Okay? Make sense? Any questions about this? Okay. Again, the same statement. Cardinality can be tricky because we have another example. Now let's look at this example, okay? We have three entity sets, A, B, and C, and we have one relationship connecting these three. And we have the kinetic constraint look like this, right? You have the 1 for the B, 1 for C, and N for A. Now I want to do the translation. I will have a single relation R with three attributes, right? Corresponding to the key of A, key of B, key of C. I think we are all agree on that. What is the key of this relation? Given this. So there are only 8 combinations, right? So let's try to go through one by one to see which one makes sense. If I have a design that with only A as the key after translation, is this correct? I kind of show you that face there, but this is not correct, right? Why? Who agree it's not correct? Who don't know why it's not correct? Who thinks it's correct? Okay. So, I mean, the reason here, right? So if you look at the kinetic constraint, right? So all it's saying is if I know the value of A and B, I know the value of C. If I know the value of A and C, I know the value of B, right? I could have a valid database instance where the value A appear multiple times. There's nothing stop me in your kinetic constraint for me to do that, right? So, and then I cannot have A as the primary key because then I'm eliminating a whole bunch of data, database instances that is allowed under your design conceptually, but not allowed here logically, okay? So what about having B as the key? The same, right? So we cannot have this. What about C have the key? We cannot have this. So we need to have some combination to use them as a key. And now I regret to put the answer right after the question. So one design that's okay here is to have the combination of A and B, the key there, as the key of R. Why? So this is easy to think about, right? So from your kinetic constraint in the ER diagram, if I know the value of A and B, I know the value of C, right? For every single unique configuration of A and B, it can only participate at most once in this relationship. That's what kinetic constraint try to tell you. Because of that, in any valid database instance in R, if I know the value of A and B, I can uniquely identify a tuple there, right? So which is actually it's okay for you to have the combination of A and B as the primary key for this relation. What about have the combination of B and C, right? So this is not okay, right? Because in your ER diagram, if I know the value of B and C, well, there could be multiple A associated with that. So this is conceptual design doesn't match this logical design. Okay? Whether you can have the combination of A and C as the primary key of R, yes, right? So it's the same thing, right? If I know A and C, I know B because of the label 1 associated with B. Right? In this case, it's okay. Can I have these 3 different attributes, A, B, and C, together as a primary key in R? Right? Clear no, right? Because it's not minimal, right? You can have a smaller subset of that forming the key. So this thing is not even a candidate key. Make sense? Can you have this? Can you just say, I give up, I don't specify a key? That's not okay, okay? In relational model, you always have a primary key for every single relation. Okay? You cannot say, I don't specify a key, so I cannot be wrong. It doesn't work like that, okay? So last one is not okay, okay? That's the translation. Makes sense, right? Any questions about cardinality and its impact on the translation? You mean for the first one, right? So assuming you have this first one, given a unique value of A, you can only appear once in that relation, right?
So how many B and C entities can have that relation with that specific A?
Only one unique pair, right? So assuming you have B1 C1A, B2 C2A, that violates that. Well, given A, you don't know which one it is anymore, right? So only one unique pair of B and C can participate with relationship in a relationship with one particular value of A. If you have this design, right?
So why A cannot be the key of R?
Exactly. Yeah. That's why we have that phase. I'm not happy for this one. Yeah. This cannot be the translation for this. Make sense? Yeah. Any other questions? It's very important to get this right. Yeah. Make sense? Yeah, sorry, cannot really hear you. You're too far away with Max. Sorry. Yeah. Can
So we have, so when you have the primary key A and B,
Yeah.
then we fulfill the constraint that if we have A and B, then we know that what is C.
Yeah.
But we also have the constraint that when we know A and C, we have to then we know B.
Yeah.
From the constraint, from the cardinality constraint, do we also automatically have to fill that?
Oh yeah, that's a very good question. So then you lose that constraint in this design. So essentially here you have two so that's a very good question. So here you have two cardinality constraints. Okay? Whenever you do the translation, you actually lose one of that. You can only enforce that by the key and once, right? And then if you say, yeah, now AB is the key, essentially you are actually missing the constraint A and C. When you do the implementation of that, you can have another constraint in SQL to say, by the way, also enforce that. But the other constraint will get lost during the translation. Sorry? Yeah. But there's no way for you to specify that in the schema, in the relational model, because you can only specify the primary key, right? Yeah. So that thing gets lost, right? So in system, right, when you're really doing that in practice, you are able to add additional constraint to also enforce that. But when you do the translation, the moment you pick one primary key, potentially you could have other kinetic constraint being lost during the translation process. Okay? Any other questions? No? Okay. So Now let's look at weak entities, okay? And how does that influence our translation process between an ER diagram and a relational model? So assuming we have this, we have our building, we have room, room locates in building, room is a weak entity connected to building. Do we need the locates in relation here after translation? So let's think about it, right? So how can we do translation? We have the building relation corresponding to building, great. We have the room relation. What is the key of room? The key of room, because of weak entity, you always combine the weak key with the strong one as a pair, right? The room can only be identified with a combination of the building ID and the room ID. So when I do the translation of the weak entity, right, so I will always have the building key there, okay? So, but once you do that translation, the locates in is not that important at all, because locates in actually is already encoded fully in the room relation, okay? So in most of the cases, when you have the weak entity, when you do the translation, you actually do not need that relationship connecting the weak entity and the strong entity. Okay, makes sense? Because all those information are encoded in the weak entity relation anyway. Okay, makes sense? Any questions? Do we agree? Who agree? Yeah. Okay, perfect. So generalization is a little, it's not as tricky as cardinality, but something you need to think about. So there's generalization. So assuming we have this thing, we have assistant, we have professor, they are all employee. Okay, we have this ether relationship connecting these three different entities. How can we do the translation, right? So there are actually multiple ways for you to do the translation. This is one way, okay? You can say employee have the primary key personnel number, right? So, and for assistant and professor, they will also have that key. Once you can do is you can have an employee table, a relation in your logical schema, contains personnel number and the name of the employee, okay? And then you can have a professor relation there, contains personnel number, that's a key, that there's nothing we can do about that. And also only those unique attributes associated with a professor. For example, here the unique attribute of professor is a level. So in the translation, you have professor relation with the personnel number and also the level for professor. For the assistant, you have personnel number and unique attribute. For example, here's area. When area will say, okay, then what's the name of a professor? You join the professor relation with employee relation, and you get that. Okay? So this is one way to do the translation. You store all those kind of common attributes in the parent class in one relation, and then you store those unique attributes as separate relations. So you could do this, okay? Another thing that you could do is to do this. You can say, okay, I store all the information associated with a professor. For professor, for second relation, I store personnel number, I store the level. I know professor is an employee, so it must have a name. So I have one professor relation stores personnel number, level, name. That's all the attributes associated with that professor. And then I could have another assistant table do the same thing, right? I could say, yeah, it has an area, has a personnel number as a primary key, and also because assistant is employee, it also has a name. I could do that. And then for all those people, all the employees who are not assistant, not professor, I have another table for them, only storing their personnel number and name. I can also do this. Okay? That makes sense. How can we compare these two? Which one is better? Look at these two different ways of doing this, right? As you can see, I mean, there's no universally right answer about which one is better. Because for some queries, it's easier for you to do in the first design, and for some queries, it's easier for you to do that in the second design. For the second design, right? If all your queries, that for every single professor, whenever we need that information, we need a name, for example. Then the second one could be a better design because every single time you process a professor, and that information is there. For the first design, right? So if you have like this way of doing that, if you need the name of professor, you're always need to join these two different relations. Okay? If you don't want to do that, what to do? You can define a view on this. That's why I've introduced the notion of view, right? So, and then you don't need to think about how the whole thing is getting organized. But underneath the cover, right? Given this design, some queries are easier. And for the second one, right? So there are also some queries that's kind of harder to run for the second one. For example, I'm going to say, okay, give me all the, tell me how many employees that we have, right? So in the first design, when you have this common table contains all the information about employee, you can just do one aggregation on that relation, right? You get all the employees. For the second one, you kind of need to union these three relations first, and then you count, right? So for different queries, it's easier to run here, right? Or like easier to run in the second design. For some queries, easier to run in the first design, right? So again, which one makes sense depends on your application. And when you're building a system, when you do not want some other user who are writing SQL query to think about this difference, you can define a view to make sure this thing is kind of hidden from whoever is writing SQL query. Okay? That's why we have view, is to make sure other people don't want to think about the difference. But when you are building your relational schema, you kind of need to think about which one makes sense for your workload. If you are running a lot of analytical query to say, yeah, I really want to track how many employees we have, if that's the only query you are writing, maybe the second one is not that good because every single time you run it into fetching information from three different places. If you have an application where every single professor must have a name, and whenever I'm showing it, I never show the personal number, I always show the name of the professor, then maybe you go for the first design, okay? Because that could potentially be faster in your system. Okay. Now let's look at this ER diagram and try to think about how we translate it. Okay, so we have been talking about this for many times now, right? So every single entity site become a relation, right? So we can have the professor, right? We have assistant, we have student, we have lecturer, right? And all those relationships on the left-hand side becomes relations on the right-hand side. Okay? And you can think about whether it makes sense to actually merge them. Okay? So this is one example, right? So when you go back home, try to look at it, right? So it might look a little bit intimidating at this moment, but it's not that hard. Okay? Understand cardinality, understand weak entity, understand generalization. You should be able to do this relatively easily. Okay? So yeah, about logical modeling, right? So in practice, you are not going to do this translation all by yourself, okay? So what's going to happen is there's a whole bunch of tools for you to semi-automatically generate a relational model from an entity relationship model. Because as you can see, the translation process, although it's a very dedicated process, there's some part that kind of automatic. Right? So each entity side become a relation, right? So and pretty much, yeah, that's always happened, right? So there are some tools to generate some baseline design for you automatically, giving an ER diagram that you draw in that tool. Okay? What people usually do is they take that tool, generate a relational schema, and then try to fine-tune it. Try to say, yeah, you don't merge this tool, but really want to merge these two relations. You merge this tool, but don't really want to merge them, right? You are picking a different way of encoding generalization. I don't like that. I want a different thing. So that is what usually happens in practice. You have this semi-automatic tool to help you to get a baseline implementation, and then you take that and try to fine-tune it. If you're curious about that, this is one example tool that you can actually use online to just see that translation process. Okay, so that's all we have for today. So on Friday, we are going to talk about integrity constraint, how to impose more constraints into your in your database using SQL queries.